I am not right, right. Well, hello everybody. I'm in California. It's 7 o'clock in the morning, and thank you for inviting me. I hope that what I have to say will be of use to you. I'm going to share my screen now, so bear with me for a second, okay? And now I need to go into present mode. Uh, So the title of my talk is Investigative Science Learning Environment, Helping Students Learn Physics by Practicing It and Be Empowered in the Process. And what I mean by empowered, that the students feel that they can do physics, that they belong in physics, and they're looking forward to physics classes. Uh, I'm sure you're familiar with the results of physics education research that over the last 25 years showed that students do not learn from listening to lectures. Traditional instruction works only for people like us who become physics professors because they are able to teach themselves. But when we use transmission mode in our instruction and students sit passively and listen to what we have to say, their learning gains are almost non-existent. And the first papers appeared about it at the end of the 20th century, and in the 21st century, not only in physics, but in mathematics, in biology, in chemistry, and engineering, the results are the same. And now we don't question anymore whether transmission or traditional teaching is better or worse than active engagement. The answer has been found empirically. It is active engagement leads to more learning than traditional instruction. But the question is, what should students learn? If we actively engage them, then what is it that they should learn? And, traditionally we focus on quantitative understanding, conceptual understanding, problem solving skills. And nobody says that it's not important. But Organization for Economic Cooperation and Development in 2018 came up with a position paper on the future of education and skills in 2030. And this is where the students who you teach will be active members of the society. And so what this position paper says, it's not just the disciplinary knowledge that we are used to teaching traditionally, but the epistemic knowledge. And this is what Martin said, that, epistemology, the understanding where knowledge comes from and how to think as an expert in a specific field. That is what is becoming important, because the factual knowledge now is used by robots. They're programmed, they do the work that traditionally people did, and people are left to do creative jobs, solve complex problems. And to do this, they need to know how the science that produced the facts that they learned, how it works. So I would say that, at least in the United States, and I'm sure you will share some of this sentiment, we talk about three major challenges in physics education, let it be high school or college. First, of course, how to achieve active engagement of all students. And active engagement means that students are collaborating with each other, they're talking to each other, they're working in groups, they're testing out their ideas in the learning process. Second, how to help students develop epistemic knowledge of the discipline. There are very many active learning approaches, at least in US, that engage students in active learning, but there's no epistemology there. They use what is the method when they ask students to read the book before they come to class, and then they have discussions of what the students read. That has nothing to do with developing epistemological knowledge. So how do we organize the learning process so students start thinking like physicists, not like physics students? And secondly, how to ensure that all students will feel welcome in physics? Again, at least in US, we have a huge underrepresentation of women in physics at all levels. Less in high school, but then in college, it's about only 20% of students in physics majors are women. And then if we go up to professors and teachers, there are even few of them. But also in US, there's a people of color who are underrepresented. So how do we ensure that everybody is welcome? And the answer to this, ambitiously, I would say, is the investigative science learning environment approach that I'm going to show you how it works today. And because you're not going to be active participants, because this whole setup is counter to everything that I'm going to do, I will pretend that you are simultaneously students and the teachers. I will tell you what students do, and you try to do your best to think like a student at this moment. It will be a very brief moment. You will not have a group to share your ideas with because of the setup, but I want you to pretend, okay? So let's play this game, okay? Okay, so we will start with a very simple example, not example, but observation that all of you had, and this is what this observation is. And I do it in class with my students, and all my teachers do it. Watch. You saw it before, right? Nothing new. You feel comfortable. It's not threatening. The question is, where does the loud sound come from? So as a student, you will get in groups and you will brainstorm what's called crazy ideas. And crazy ideas means they don't need to be right, but they need to somehow explain or produce an answer to this question. And I mean an answer, not the answer. I'm not asking for the right answer. Okay, so think about it for a second. Where does the sound come from? Well, the balloon pops. There's air inside, so students usually, the first idea that they come up with that this is air. Okay, that's a great idea. And we call it, this crazy idea, a hypothesis in physics. So I say, okay, how do we test that this is air? And we tell the students that to test the hypothesis, it means to accept it as true, even if you don't like it at the moment. Design an experiment whose outcome you can predict using this hypothesis, run the experiment, and compare the outcome to the prediction. So the students get together, think of an experiment, and usually they come up with an experiment. Let's fill the balloon with something else other than air. Let's fill it with water. If air is responsible, there should be no sound. Great. I have this water balloon already prepared because I know that they will come up with this idea. So great. Or I can give them water balloons to every group if I have enough. So here is the experiment that they predicted the outcome. There should be no sound. Well, there's a little bit of sound of splashing water, but nothing like what we saw. Okay, does it mean we proved that it was air that made the sound? Well, then again, I become a teacher and say, well, in physics, one experiment does not is never considered a proof. So you need to run another one. So can you come up with another experiment for air? Because it looks like we're on the right track. So they come up with a new experiment that let's take a plastic bag. So we'd have no rubber. If this is air and we poke it with a needle the same way, if the air is the only thing responsible, it should make a loud sound. And to be honest, I never thought about this experiment until my students came up with it. So we do the experiment. What do we take? A good thing is a plastic bag, like a shopping bag, where you go to a supermarket and you can put your fruits and vegetables in it. So I always have a few of these plastic bags and we do the experiment. No sound. Uh-oh. It looks like air is not that good of an explanation. So what else is there? And students come up with an idea that it's the rubber because it's only the air and the rubber in the balloon. Okay, it's the rubber and we poke it, it should make the same sound. So take the rubber, stretch it, and poke it. Oh, there's some sound, some good sound, but not as the balloon. So they get in groups again. So where does this sound come from? And they come up with a new idea, especially when they look at the original balloon that I poked, that it actually is in pieces. And the plastic bag was not in pieces, it was just one little hole. It's the rubber that breaks instantly and releases the air quickly. That makes the sound. That's the new explanation. How can we test that? Well, that's a difficult one, but the students again come up with an idea very quickly. They say, well, let's take the shopping bag, the plastic bag, but not poke it with a needle, but make the air escape quickly by clapping. So if it's the quick escape of air, we should get a much louder sound than when we poke it with a needle. Okay, and we do it. And we do it. And it is a loud sound. And I usually invite some other student to do the experiment, not myself. And that is really a surprise for them to figure out that both the air and the rubber are important. And you're probably thinking, well, that was easy, right? It's just the balloon, that's a joke. What about a more difficult idea? So I am going to show you a more difficult example. And I know that not all of you teach this topic, but it's even better that you don't teach it because you will be like students now for sure. So imagine that you, as a student, learn kinetic molecular theory, and you know that air consists of molecules, right? You teach it to your students. You imagine that you learned electricity, magnetism, and electromagnetic induction, and you know about conductors and dielectrics, and you're familiar with ionization of air and other gases, okay? And you learn optics, and you learn the wave model of light. You explain the behavior of light using the electromagnetic wave model. So for now, you are convinced as a student that light behaves as a wave of alternating electric and magnetic fields, okay? So now we start. So we start by observing a very simple experiment. Okay. Pay attention. Uh-oh. Oh, it's playing. This is Dina, my student. She's a physics teacher now. Somebody has a dog. Can you please mute yourself? So the students observe that a negatively charged electroscope gets discharged with a UV light. So they get in groups and try to figure out what happened and how to explain it. And the first crazy idea that they come up with, that UV light ionizes air, and then air is made of ions, and then the electroscope is charged negatively. So the positively charged ions go to the electroscope and discharge it. Well, if this is a correct idea, then, and we take a positively charged electroscope, it should discharge too, because then the electrons in the air would cancel the charge. So we run the experiment. So now Dina takes a positively charged rod and charges the electroscope. So if she shines visible light, nothing should happen. And if she shines UV light, it should discharge. According to this explanation, you don't need to like it, but you need to make a prediction based on it. So visible light does nothing, so we feel good. At least it works in this way. And now we take the UV light. There's nothing to. Well, that's a surprise, right? So it must not be ionized air. We rejected this explanation very solidly with this experiment. So the students go back to the drawing board and they come up with a new explanation that it's not the air that discharges the electroscope, but maybe the UV light kicks electrons out of the negatively charged electroscope. And then they go away and the electroscope becomes positively charged. Well, if this is correct, then the neutral electroscope, and it discharges. So if this is correct, then the neutral electroscope, if we if we send UV light, it should become positively charged, right? So if the negatively charged electroscope discharges because extra electrons leave, then the neutral electroscope should charge positively. So we do the experiment. Doesn't. The UV light does not charge the neutral electroscope. So here we can say, well, maybe this is a wrong idea, then we rejected it. But now we start thinking, okay, what if it does charge the electroscope, but electrons now that leave are attracted back to the positively charged electroscope? The explanation is still correct, but our assumption that the electrons will go away needs to be tested. Okay, so how do we do that? We need somehow to pull these electrons that came from the electroscope away from it. And how can we do it? By using a positively charged electroscope. So let's do it. So we will take a positively charged electroscope and we will put a wire mesh on top of it. And we're going to charge it positively. And then we will take, so now this is a positively charged electroscope, right? So now we will take a neutral electroscope with a zinc plate and shine the UV light on it. If our idea is correct, then the electrons will come out from the neutral electroscope and be attracted to the positively charged electroscope. So the charge on the positively charged electroscope should decrease, which it does. Did you see it? So this is before the UV and after. On the positively charged electroscope, the charge decreased and our neutral electroscope got charged. So to make sure, we need to check what charge our neutral electroscope has. And how do we do that? We do it by doing the following experiment. Just bringing a positively charged rod to both electroscopes. And if they are positively charged, then bringing the positively charged rod will increase the charge because more electrons will get attracted to the top. So now we figured out that light, UV light, does something to the electroscope, to the metal plate zinc. It removes electrons from it. And this is the beginning of a completely new phenomenon that led to the creation of the quantum model of light. And the process that we went through is at the heart of the investigative science learning environment approach. For every idea that the students need to learn, they start with simple observational experiments and they identify patterns in them. And this is, the sound of the balloon. They come up with an explanation and they have to test it in a new experiment that they design. If the outcome does not match the prediction, they need to make a prediction before they run the testing experiment based on the explanation that they're testing. So if the outcome does not match the prediction, either propose a new explanation, as in the case of air, for the photoelectric effect, or check assumptions, as in case of trying to discharge the neutral electroscope with UV light. But once we get the agreement, we need to run more testing experiments, like with the air for the balloon, and then we can proceed to the applications. And we wrote a whole book how to do it. It's called Investigative Science Learning Environment, published by the Institute of Physics. And we have a textbook, algebra-based, called College Physics in the US, but college doesn't mean it's for college. It means for any course that does not use calculus. But then we can look at what difference does this approach have for understanding the epistemology of physics. And the most important thing, one of the most important things, is that our approach to experiments changes. Instead of them being demos or labs, they become observational experiments in which students learn to identify patterns or learn enough about the explanation to develop a model, testing experiments to test the model created to explain the observational experiments, and application experiments to apply multiple tested models in order to solve the problem. So an example of observational experiments, you saw it twice, but I'm going to show you one more, for example. Let's say you have a light bulb and light emitting diode. So an observational experiment would be to make a circuit to light them both and find the difference in the behavior of the light bulb and an LED. You don't need to lecture to the students. They don't need to know anything about semiconductors to be able to do these experiments. And that's the beauty of IEL, that you do not, as long as the students know how to make electric circuits, they can find all of the most important properties of LEDs just by doing this simple experiment. Once they find what happens to the LED and the light bulb, they need to test to propose explanations and test them. And usually students propose two explanations for the behavior of the LED that only lights when the current is in one direction. And we only thought originally about Natasha's explanation, that the LED conducts and glow when current through it is in one direction. But then the students proposed a different explanation, that the LED conducts current in both directions, but only lights when the current is in one direction. So they have to test it. They come up with the experiments, they run the experiments, and they realize that they can reject Eugenia's explanation and only Natasha's explanation remains. And after they learn about LEDs and their properties and study them some more, I'm not showing you the whole sequence, they can solve more complicated problems, which we call application experiments. And if you think about the history of physics, that's exactly what happens. I'll show you a little later how history of physics and epistemology of physics matches this process. So I'm going to give you a few more examples of observational experiment. For example, design an experiment to find the relation between a potential difference across and current through a commercial resistor. Students discover the linear dependence without knowing anything about it before. Then they can test whether this relation applies to an incandescent light bulb. Again, they don't need to learn anything about an incandescent light bulb. If they can make electric circuits, they can do these problems. This, the last one, is an application experiment, and it's much more complicated and can only be done after students understand how light bulbs work and how LEDs work. So that brings us to another aspect of the investigative science learning environment, is multiple representations. Traditionally, we teach physics mostly with two representations: language, words, and algebra or calculus, mathematics. So it turns out that there are many more representations that first physicists use, like graphical representations. Think about the role of Feynman diagrams in the development of quantum chromodynamics, for example. But the students need these graphical representations to build the bridge between words and algebra. So cognitive science tells us that if we do not start with algebra first, but we start with phenomena and graphical representations, the students can develop physics concepts much more successfully. So we have a whole library of these representations that are motion diagrams, force diagrams, energy bar charts, momentum bar charts. Like for every concept, we have a graphical representation. And most importantly, that throughout this process, students work in groups, in small groups, but they share what they found with the class because they have these small whiteboards about this big. They write on these whiteboards with colored markers. Then they lift the boards. Everybody sees what every group came up with. They have a discussion. And this is how a learning community is created. And they have opportunities to improve their thought process and work without punishment. You saw this improvement a little bit as I showed you with both the balloon and the photoelectric effect. But in fact, our students can resubmit their lab reports, their quizzes, their tests, and they're not punished for the second or third attempt because we encourage them to work harder and persevere. I gotta take a drink. So we can say that the IL approach is an example of an intentional approach to curriculum design. So what does it mean, intentionality? Intentionality of a curriculum or whatever you do in the classroom means that the product of knowledge cannot and should not be separated from the means by which it came to be known. So if you are lecturing to the students and saying, this is Newton's second law, this is how you solve the problem, then the process is listening to authority. And the product is Newton's second law. And so if you do this, not you personally, but if one does this, then they need to acknowledge that for their students, physics is like a Bible, comes from the physics God, and they need to believe it, and then they need to practice it, which is not what physics is, which is a science. So we have two intentionalities that we put into everything that we do in IL. First, intentionality is about what and how students learn. If we want students to learn the process of physics, they have to be engaged in this process. And second, it's important how students feel about physics. And the intentionality is that students are motivated to learn physics, that they are empowered in this process, and they see it as an opportunity for mental and spiritual growth. So how do we do that? By helping them learn physics by practicing it in every class, and by helping them develop confidence and growth mindset. So where do these intentionalities, where did they come from? From history and philosophy of science and the studies of brain development, cognitive studies, and motivation. So let's go back to our photoelectric effect example. If you know history, then you know that the whole study of photoelectric effect came from the accidental observation of Henry Hertz, who was trying to test Maxwell's equations and accidentally saw that the two charged spheres produce a discharge between them much faster when the sun shines on them. And when they're covered with glass, he needed much more charge for the spark to go. He said, that's an interesting thing, but I'm not going to investigate it. I have no time. So Wilhelm Holowachs did the experiments similar to our electroscope experiments, came up with an idea that electrons leave, and then Alexander Stoletov in Russia and Philip Leonard in Germany continued conducting quantitative experiments. So they were all observational experiments. Many tried to explain the patterns that Stoletov and Leonard found, including Leonard himself, but they failed to account for all of them. So Albert Einstein took Planck's idea for the black body as an assumption that light is not only emitted by portions, but absorbed by portions, applied it to the explanation of all the patterns of photoelectric effect, and was successful. But Robert Millikan said, that's not right. Light behaves like an electromagnetic wave, not like a stream of quanta. I'm going to prove it. I am going to show that the predictions based on Einstein's equation for the electric effect do not work in the experiment. He spent 10 years trying to disprove Einstein's explanation and failed to do it and got a Nobel Prize for it, for the failure to reject. And after that, as you probably know, photomultiplier tube was invented, which is the foundation of all practical applications of the photoelectric effect by Kubetsky, Lantz, and Salzberg. We can put them on our little chart, and we see that the science historically follows this path. What about in real time? Do physicists work this way through the processes similar to the IL sequence in real time? So we gave physicists a problem where you have a tank of water and you put it on a sheet of white paper and you shine a laser pointer on it. You need to in order to see this beautiful light cone better, you just need to dip your finger in milk and put it in water to have a little more scattering. The phenomenon is amazing, but how do we explain it? So we gave this to practicing physicists who are actively publishing, and we video recorded them and analyzed what they're saying. And it turns out that they went through the processes similar to the IL process exactly. And as you can see, when one person talks, it's red. When person two talks, it's blue. But when they are talking overlapping together, it's purple. Look how much purple it is. It's a collaborative process, right? And how they go from observation to patterns to hypothesis, designing experiment, making a prediction, performing and testing, and then making a judgment, considering assumptions, drawing representations, and other is the applications that they talked about. So it goes again and again and again through those cycles. So they work like this in real time, and we did many groups and they all resemble the same pattern. Turns out that our brain works in a very similar way. So as you know, probably we have a sensory part, cortex, integrative, and the motor cortex. And so what happens, let's say you walk into a dark room and you see some yellow light. You very quickly stretch your hand to touch it. So what happened? You saw the light, it's the sensory part of your brain here is activated, and you start reflecting on it. It's called reflective observation on the concrete experience. Like, what can it be? Oh, it's yellow, so it can be a candle. That's your abstract hypothesis. And you stretch your hand to actively test it right away. So for the brain to learn, it has to go through all these steps: concrete experience. Let's say you're sitting in lecture, you're listening to a lecturer. That's concrete experience, right? That's sensory cortex, but you don't have time to reflect on it. You don't have time to make your hypothesis, and you don't have to do time to have active testing, which involves a motor function. A motor function means you have to talk about it, you have to do something, you have to move your body in order to test your ideas. As all these parts are absent from traditional instruction, no wonder that it doesn't work as effectively as active engagement. Why did it work for you? Why did you all learn from lectures? Because you did all these steps on your own or with your friends when you went home. So cognitive science tells us that learning is a social process. People do not learn by themselves. So you need to talk to somebody. Remember all your buddies in physics classes with whom you argued and discussed things to understand. There's also a lot of work on fixed or growth mindset. Fixed mindset means that people think that the intelligence is given and nothing can be done about it. They're rather smart or dumb. They can do or cannot do. Or a growth mindset that says, well, intelligence develops. There's books written about it, papers written about it, that says that if you let people see how they can improve their work, they develop growth mindset. And lastly, perseverance is one of the most important predictors of success in life. And perseverance means you do the same thing again and again. You don't quit if it doesn't work. If you look at traditional, I'm not going to say anything, I'll say it in a second. The question is, do we need to teach the IELTS process to the students? Well, mentally raise your hand those who have children or grandchildren or younger siblings or just observe children in the outside. You also did, right? Kids eat dirt. Why would they eat dirt? Well, we can explain it using everything that we learned about IELTS and the nature of science now. Well, they see dirt. That is an observation, that's a sensory experience. They reflect in their brain what looks like that. Oh, chocolate looks like that. So they form a hypothesis that dirt is chocolate, and then they design a testing experiment. They say, well, let me eat it. And the prediction is that if it is chocolate, it will taste like chocolate, so they do it. And they do much more. They are skilled in testing ideas experimentally. They persevere. If you observed them trying skateboarding or jumping on bicycles, it's amazing how they do it again and again and again. There are YouTube videos about 5-year-olds trying to do a trick on a skateboard that would blow your mind with their perseverance, and they work together. So why do they do it for these things, but they don't do it in our classes? Well, not only because they have the need to know, but I'm going to say something very controversial, that the problem is that traditional and even reform teaching goes against much of what we're good at and much of what we know what helps people learn. For example, we give students answers before they have questions. So there's no need to know. And the need to know is the key motivation for learning. We grade them without allowing them to resubmit their work. So they have no opportunity to try without being afraid to fail. And if you want to do a trick on a skateboard or serve in tennis or play music, you need to be able to fail. We preset the pace of the curriculum, so we punish those who need more time. Sometimes we grade on a curve, then we punish them for collaboration. We give them traditional problems on multiple choice tests. We punish them for needing to reason with something other than mathematics. And it's important to understand that all these issues are much worse for women who start with an imposter syndrome. So what's an imposter syndrome? It's knowing or feeling inside that you don't belong, that everybody else is better than you, that they can do it, but you cannot. When you have the imposter syndrome, it's very difficult not to quit. So what is the solution? The solution to all these problems, I would call universal design for education. And I just want to share a little bit what the term universal design is. I learned it myself recently, about 5 years ago, when I met a professor of disability studies. So if you Google universal design in education, the Wikipedia says, it's the design of buildings, products, or environment that makes them accessible to all people, regardless of age, disability, or other factors. And, in examples of universal design, I don't know how it works in Uruguay, but in US, we have ramps to go off the sidewalks. So if you are in a wheelchair, you can roll off. We have these little bumps. If you're blind, you can use a special stick that feels the bumps and you know the sidewalk ends. In the elevators, we have buttons that are with Braille alphabet, so you can touch and know what floor you need to go. We have ramps to go into the buildings and so on and so forth. So now these are, at least in US, standard features of the environment. I don't know about your country. Do you have these? Somebody should nod. No, we don't. Or yes, we do. Does Uruguay care about having all buildings and all roads accessible to all people? Okay, I'm not seeing any reaction from people who I see on my screen. Okay, I assume it does. So what I'm trying, and you're saying like, what does it have to do with learning physics? Yes. Okay, 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 good, 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 great, great. Okay, perfect, perfect. So you're thinking like, what does it have to do with learning physics, right? This is about buildings design. Well, if you think about how many students hate physics, are unsuccessful in physics, drop physics, do not want to take physics, you might start thinking that physics is only for very special people and everybody else it's inaccessible. So universal design for physics education should have a goal to make physics accessible to all students. When other people, your friends, or new people who you meet, ask you, what do you do for life? And you tell them you teach physics, what is their reaction? I asked many people, including myself. The reaction is always the same. Oh, you must be smart. Oh, I hated physics when I was in high school or in middle school and in college and kindergarten. I just hated it. So difficult. We have what's called this brilliance trap that we created ourselves, that only very smart people can do physics. And that makes physics very exclusive. And in US, mostly the preview of white men, and probably in Uruguay, just men. And all others are excluded because they are physics-wise disabled. We make them disabled. So how do we make physics accessible to all students? I would argue that ANII is an example of the approach of universal design for education. And this is not my argument. This argument was made in a book by Julie Mabey, professor of disability studies, who observed my classes, talked to my students, and came up with this conclusion, which I myself would have never come up with because I didn't even know what universal design was before I met her. So why is ANII an example of universal design for physics education? Students start on the same page. They observe simple phenomena, so nobody's privileged. They do not use fancy language when they come up with their crazy ideas. We specifically prohibit the use of scientific language, only the language that a 5-year-old can understand. They use multiple representations for help. They discuss ideas and test them right away. They progress at their own pace, and they improve their work without punishment. And they become a part of a community with shared expertise. So why does it help them to be included and successful? Because starting on the same page and not using fancy language develops confidence in everybody. I can do it. Using representations and discuss ideas is based on how our brain works. So we are using the processes that our brain does naturally. We progress at our own pace and improve without punishment. That develops growth mindset. And that means if you have a growth mindset, then you start thinking, I can do it. If I can do it, I just need to work a little harder. So I'm included. I'm not excluded. I'm not disabled. And community and shared expertise helps avoid imposter syndrome, and productive habits set you up for life. So you are probably thinking, what does it look like? That's what it looks like. You can see these are high school students. Here, I think, are middle school students. These are future teachers. These are undergraduate students. They all work in groups. You see the whiteboards, right? So they work on the whiteboards. They share ideas. And on the top right, you see students walking around to other groups because they're building a community. So what's important is that we can apply the ANII process to every concept. And the labs that are usually an add-on to our lectures now become the most important part. Students do the experiments first, then you talk to them about it, and then they go back and test the ideas. So the laboratory experiences is the foundation. What if you don't have equipment? You can have, we have materials online, you can show them videos, or you can do an experiment and engage them in the discussion. So it's not necessarily that they do the experiment themselves. Here's an example. We give students scales and we ask them to pull them, one person or both people, and notice what the scales read. You see that the scales are different. They have different, they see different scales. But no matter who pulls, the reading is the same. So what's the pattern? How the scale reading are always the same. How can you explain it? Well, to explain it, we need to draw a force diagram. So that's what students are asked to do. And they draw the forces that scales exert on each other and come up with an idea that the forces are the same. And they say, well, you know, it's the same for the scales. We need to form a hypothesis that it works for everything, but that's ridiculous. Of course it doesn't. Two objects cannot possibly always exert the same forces on each other. Think about a collision of a heavy truck and a light car. The heavy truck moves on, the light car is smashed. So they say, okay, go rule out this idea, reject it. And we give them cards. Here, the cards have plungers, so you don't see the computer screen, but our cards have sensors and force sensors, and they see the graphs of force versus time on the computer screen. And I'm going to show you the experiment. So you have cards of different, that you can load different objects. So this is a light card. And here you have a heavy card approaching. Oops, here. And it's loaded with bricks. And so the students design an experiment. Let these two cars collide. And what their crazy idea predicts that the force reading should be the same, but they don't believe in it. They think that the heavier or the faster moving card will exert a larger force. And so they do the experiment. And here, a proxy for forces are the plungers. Watch the plungers. See, at any moment, the plungers are compressed the same way. So they get the graphs on the computer. And no matter what they do, the graphs have the same amplitude, the same magnitude at every instant. So they just invented Newton's third law all by themselves. And they try to reject this idea. Oh my God, they work so hard. They take different cards. They make them move in the same direction. One is catching up with the other. They move towards each other. They put all kinds of things on bumpers, and they cannot do it. And so this process goes like that, from simple observation to the formation of an idea and to testing it. And this is our lab handout for the experiment, for this idea. So they have interacting scales, and then they test exactly what we just went through. This is on one page of the lab handout. But what happens in the class after? In the classroom, you can have a discussion about what these forces are like. And this is one of the questions that stumps a lot of people. A book sits on a tabletop. So that's a tabletop and that's the book, right? What forces the Newton's third law pair to the force that Earth exerts on the book? Choose the correct answer with the best explanation. The force that the table exerts on the book, because it's equal and opposite in the direction to the force that Earth exerts on the book. The force that the table exerts on the book, because the table and the book are touching each other. The force that the table exerts on the book, because it describes the same interaction. The force that the book exerts on Earth, because it describes the same interaction. Or the force that the book exerts on Earth, because it's equal and opposite in direction to the force that Earth exerts on the book. Well, the most common answer from the students who learned about equal and opposite is E, that it, and it's correct because it is, the book exerts on Earth, but it's not because it is equal and opposite. We can have a lot of equal and opposite forces that are not forces of Newton's third law. Newton's third law describes the forces describing the same interaction. And so this is what you discuss with the students after they constructed and tested their ideas. And when students design their own experiments, they are guided by questions that tell them what to think about, and rubrics that help them self-assess their work. Now, I'm going to stop because it's been an hour. We started much later than I expected. And the question is, should I go on or should I stop and ask and wait for questions? What is your protocol? I need about 10 minutes that were spent at the beginning to check the translation.
Sí, por favor, que continúe, sí.
Yeah, okay.
Yes.
Go ahead. Yes? Okay.
Go ahead.
Okay. So to help students think about the right stuff, we came up with what we call scientific abilities. Scientific abilities is what physicists do when they do physics. So they represent information in multiple ways, design and conduct an experiment to investigate a phenomenon, develop and test models, design and conduct testing experiment, conduct an application experiment, collect and analyze data, evaluate models, equations, solutions, and claims, and communicate, right? We came up with this list talking to physicists and observing their work, and we realized that these are important things for the students to learn. So we created questions that are based on these abilities that we want them to develop that help students what to think about, not what to do. So when they design testing experiments, we tell them propose experiments to test the explanations, but do not perform them, and use them to make a prediction. No, do not use your intuition, but use the explanations. That is the most difficult part in making a prediction, because everybody wants to predict based on their intuition, not the explanation they're testing. And we also created scientific abilities rubrics that the students have in their lab notes or class notes. And these rubrics help them self-assess their work before they submit, or when the instructor gives feedback using the rubric, they can go back and revise their work. All these rubrics are publicly available. You can go to the website and download them. I won't spend much time discussing, but I want you to know this is all free for everybody. So the rubrics are all written based on the same approach. Missing, it means a student doesn't know that they need to do it. A student not adequate, a student knows that they need to do something but have no idea how to do it. Needs improvement means a student writes relevant things with some minor omissions, and adequate means as perfect as it can be. And this is like an obvious thing. Of course, students should do that. But the question is, or the issue is, that we ourselves very often have no idea what adequate looks like. What is it that students should do to please us? We provide feedback when they do something wrong, but we never tell them exactly what we expect. So our rubrics tell them exactly what to expect. So now I want to share a small study about the students. You are wondering, like, how do students respond to that? David Brookes is one of the developers of ANII, and this is the result. The study is the result of the interviews conducted with his students about the physics class. These are the words that came from them, and the questions were very vague, like, why did you take the class? How does it compare to other classes? Would you like to talk about it? When the students answered, say, like, what do you mean? Can you be more specific? So it was all very, very general. And so the students were videoed and we produced a transcript. The transcript was 200 pages. So what we did, and there were 17 students. So what we did, we read this, what the students said, and we found the themes that they're talking about. And it turns out that the interviews lasted from about 20 minutes to about 80 minutes. And there was a lot of themes mentioned. Females talked about more themes and males about fewer themes. And so we identified the most common themes. So the theme that every single student, and they were all different, some got C's, some got A's, some got B's. Everybody talked about the transfer. So they talked about how they could apply this physics knowledge and representations and reasoning and ways to study either to other subjects or to the outside activities or their future jobs. Every single student, unprompted, talk about it. And here is, one of the quotes. I shortened it. So if I'm in class where the professor, like a robot, just talking and reading PowerPoints, I can go home and turn it into something that is going to be interesting to me because you guys, the teachers, made us think about how we learned and what is the best way to learn for us. So learning how to learn is the most important thing in every course. And this person is talking about it. Also, almost 90% of the students talked about the role of experiments, how experiments help them learn. They say that, by the way, they will learn this thing. It's not as hard as what regular physics students. Remember, we talked about the imposter syndrome, that you don't belong, right? They think, oh my God, this equation is difficult to derive and this and that. But in our class, we're like, well, it's easy. Because if you grasp this and this, you think about the situation when you get this, and it's cool because we got to do all those experiments and we understand already how it works. So the experiments are needed to understand how things work, not teachers talking about it. Opportunity to figure things out. This is a really cool quote of a person who didn't like it at the beginning. It was a learning process because I was so used to be fed information and remembering it and repeating it that here at the beginning, I didn't like it because I was not shared information. I said, what the heck is this? How am I supposed to learn anything if the professor didn't tell me anything? And I was so you're so accustomed to being fed all this information and memorizing that you have no idea what's going on. Here, I have to figure out what is going on, and then a true understanding could arise. This person could have written a book on cognition, right? Another important thing that a lot of them, mostly women, but even men, talked about affect, about the emotional engagement. I definitely do enjoy physics. I enjoy biology for other reasons, but it's just because I love animals. So it's a different reason. But in terms of interaction and stuff like that, I like physics a lot. And it really does. At first, I come to class and I'm like, oh, what crazy things are we going to do today? Let's see what happens. And then when we're actually doing it, I'm just so hyped and I'm so excited. And magnets, I love magnets. My magnets, oh, those are my babies. I love magnets. Both magnets and with mirrors and with lenses. It was exciting. It was cool. It was like I knew I was going to leave with something that was going to blow my mind. Just think about it, of your students thinking of magnets as their babies. Won't it be cool? And they talked about group work and importance of the community, developing confidence, participating in problem solving, and knowing where things came from. These are the most common things. Remember, they were all unprompted. We didn't ask them about it. I have long quotes about learning in the pandemic, but I'm not going to read them because they basically say the same thing. But what I want to say is that we have studies that show that IELTS students persevere. And as I said above, grit is one of the predictors of success. We find that designing their own experiments develop perseverance while doing traditional labs does not. On average, the time spent by IELTS students making sense of experiments, designing and analyzing data is 4 to 5 times longer than for the students in traditional book labs. So they persevere even when they can leave. That's in college, when they can leave anytime they finish. Students in traditional labs leave when they, 40, 50 minutes at after the beginning, and IELTS students stay for 3 hours. We also have studies about their high gains on standardized tests, how they spontaneously use representations, how they design experiments, collect and analyze data, evaluate assumptions, communicate. We have all that. But what we also have is student understanding and belief that they can be successful, they can learn, and they belong in physics. Well, it's not easy, right, to do it, because instructors need to learn to think about physics as students learning differently. They need to act differently in class. You're not the actor on the stage anymore. You're helping other people learn because it's their brains they need to change, not yours. Students need to think about their learning and instructors teaching differently. They need to act differently. They should not expect you to give them the answer, because to give them the answer, you basically need to cut out a part of your brain and transmit it into their brain, because answer is the brain connections in your brain, right? So the whole idea of give me the answer or explain to me is an oxymoron. You cannot do it. Lots of research shows that both are very difficult, not only for the students, but mostly for teachers. We have tons of resources. Many of them are free. I will tell you what is free, and you can start using them. So first, we have a lot of people working, or those who worked before, like Alan Van Heulen retired 10 years ago. He's not a part of the team, but he contributed at the beginning. We have the book. It's available online. I'm sure the university has it. And it's a PDF document. They can share it with you. We have a textbook. It's not free, but the active learning guide and online learning guide with activities for the students are free. Instructor guide is free. And the videos that we put into the textbook and the active learning guide, the videos of experiments, are all free. We have the website with scientific abilities, rubrics, and labs, and other tasks. It's free. We have the site with the videos of experiments with the questions, and the YouTube channel. You can find the IL YouTube channel. It doesn't have questions, just the videos. There are games, the universeandmore.com, that are IL based, and oh my God, over 1 million people, no, over 10 million people played those games. So a few points to take away. Learning means the change in the brain of the learner. So that means doing what I'm doing now is pretty useless, right? We need to engage people in the reflection, forming their hypotheses, and actively testing them. So, because this is what the brain cycle does, it proceeds from sensory experiences to reasoning and to motor function. So it's the learner's brain and the body actually that needs to do the work. Scientific inquiry engages in similar processes. I showed it to you through the history of photoelectric effect, for example. And the IL process is the path that real scientists take. I showed you the study of physicists solving the light cone problem. And our research that I shared shows that students can participate in the real making of science, and they reflect on it and they understand how it works. And the IL approach is designed to empower all students to learn physics. It's an example of the universal design for education. So thank you. You know, there's my email. You can send me an email with the questions, but I forgot to put on the slides a very important thing. We have a Facebook group of people who are using these materials. It's called Exploring and Applying Physics. So if you're on Facebook, find the group Exploring and Applying Physics and ask to join and answer the question, and you will be a part of a community that has almost 1,200 members. I know Martín is a very active member of this group. Well, thank you very much, and I would love to take your questions.
Bueno, muchísimas gracias a la profesora doctora Eugenia, y ahora la charla es de ustedes, así que abran sus micrófonos y hagan sus preguntas o comentarios en estos minutos que tenemos.
No sé si
Daniel,
puedo,
adelante.
Martín, ¿sí?
Adelante, Daniel.
Bueno, buenos días para todos los que no me había visto al principio. Bueno, lo primero que quisiera hacer es agradecer enormemente a Eugenia por su tiempo y por su generosidad de estar hoy con nosotros acá. Y la pregunta que le quería hacer, muchos de los que estamos escuchando esta charla, trabajamos en la formación de profesores aquí en Uruguay. Y la organización de los cursos introductorios de física tiene, digamos, como dos grandes vetas. Uno que serían lo que quizás ustedes llaman conferencias, y por otro lado los cursos de laboratorio introductorios. Y yo le quería preguntar si ese formato también es el que ustedes usan en su lugar de trabajo, y eventualmente si hay alguna diferencia de la aplicación de ISLE en esos cursos. Gracias nuevamente por su generosidad.
It's a very good question. So when I prepare physics teachers, I have 3-hour classes. And these are my teachers. They have an undergraduate major in physics or engineering already. So I am not supposed to teach them physics. They're supposed to learn it in their undergraduate courses, but as all the courses are taught traditionally, they don't learn it really to be able to help others learn, right? So I have chunks of time once a week, 3 hours. And in these 3 hours, we do these activities as I showed you, like the exact process from the active learning guide. They do them as students, and it means that the experiments are interspaced with discussions. They have whiteboards, they work in groups, they do everything as high school students for, let's say, the first couple of hours. And then we reflect on what happened. And also we reflect on what I did. It's very difficult for me because sometimes I have to stop myself and say, look, this is what I just did. Why did I do it? We reflect, and then at the end of the lesson, they reflect on what they learned in terms of physics and what they learned in terms of how to help students learn. The term teaching is actually prohibited because teaching does not mean learning. So we talk about student learning. Then they have a homework that they work on and submit online. And I read this homework the day of the submission, which is about 4 days before the next class. I return it, they have to resubmit it, and then resubmit it again if it's not perfect. And perfect for every student means different things, right? This is about lesson planning and projects and everything. And then if I see that in the majority of the homeworks, there is an issue in physics that they don't understand, I have a review session before class. I say, okay, like at 3 p.m., well, class is at 4, at 3 p.m. we get together and we'll talk about it. Everybody who wants to come. Before I would do it in person, which was difficult. Last year I did it online. It was much easier. We would get together on the weekend and spend like 2 or 3 hours working on problems in addition to, and this goes for the first half of the semester. The second half of the semester, they do what's called micro-teaching. Micro-teaching means in groups of 2 or 3 people, they design a lesson, not a lesson, or a whole thing for 3 hours, and then they become teachers in class. Everybody else is a student, and then they reflect. But in order to do this, they work with me for about 3-4 weeks, first on their own understanding of physics, and then on how to turn it into a good lesson. And then when they teach the lesson, I have a very cruel technique that I developed that only works for people with growth mindset. It completely destroys people with fixed mindset. When they teach a lesson, let's say the lesson is going on and you are a student and you ask a question. And I, as a teacher, I am the student teacher, right? I did not hear the question. I just continue, right? Eugenia says, stop, rewind. The student who asked the question needs to repeat the question, and the student who is the teacher needs to respond. And if that teacher cannot respond, then the whole class brainstorms what to do. Or the teacher is, the class is going on, and the person who is the teacher says something that is incorrect. I say, stop, rewind. I ask the class, did you notice what Martín just said? And they usually say no, because as students, they're focused on their own stuff, right? I say, okay, Martín, repeat what you just said. The student repeats, the teacher, right? And now people see that there's a mistake. How do you fix it? How do you say it differently? Or a student who is teaching asks a question like, what is the answer? This is a prohibited question. We never ask what is the answer, but because it assumes that you need to know the right answer. The right way to ask is, what are you thinking? So every time when they say, what's the answer? I stop and say, rewind, and they say, oh, shoot, what are you thinking, right? So I use this opportunity of their micro teaching, and micro means they're teaching to their peers, as like a flight simulator for pilots. You know how they use a computer simulator to fly a plane, so if they crash it, they get up and fly again. Teachers usually don't have this opportunity because, the train has gone. You already made the mistake. You already didn't hear. You already misunderstood the student. Here they have this golden opportunity to focus on what the students are saying or what they're saying and redo and improve. So not only the students have to develop growth mindset, but if a teacher doesn't have a growth mindset, that's the end, right? You all have it. That's why you're teachers. You believe that you can be better. And that's what I'm trying to develop in my students. And so when people say, is being a teacher like a natural gift, you're born with it, you're a naturally born teacher, or you're a made teacher, I say that it's not an appropriate question. Of course, you have to be born with an interest in people, right? You cannot develop it. You probably need to be born wanting to help other people, but everything else is you learn, like you learn to play music or tennis or skateboard or whatever, right? But you need to have an opportunity to fail. And that's what I give my students. Did I answer your question?
Sí, muchas gracias, Eugenia. Simplemente una cortita más. Cantidad de estudiantes en esos grupos, supongo que son pocos, pero aproximadamente ¿cuántos estudiantes?
That's a very good question too, which opens up a whole can of worms of how United States prepare physics teachers. An average American university certifies one physics teacher per year. Most American universities do not prepare physics teachers, and they do not have any special programs for them. They usually prepared with math and science teachers, sometimes all high school teachers together, because there's so few of them. My program is absolutely unique. It is the only program in the United States that has multiple 6 courses, 6 3-credit graduate courses, and 3 credits means 3 hours of in-person meeting per week, in how to help people learn physics. And they also have 2 years of practice, of teaching practice. As they are in the program, they first teach in a college course, in the Rutgers college course that is reformed using the IEL approach as lab instructors and problem-solving session instructors. And then they have a lot of teaching practice in the schools with the students, with the teachers who graduated from the program. So it's a very unique organism. And we are one of the largest programs in the United States. We graduate from 6 to 10 physics teachers every year. And it's huge in the United States. These are people who go into physics teaching. And what is important about these people, that they go into physics teaching and then stay in the profession. The attrition of my students is about, after 15 years, is about 10%, which the average in US is 60 to 70% after 10 years. Attrition, it means they leave the profession. But in these courses, I not only have future physics teachers, I have what's called master's students. These are physics teachers who, my program is a master's program, who are certified to teach physics, but they don't have a master's in education. They have an undergraduate in physics, and they go through this separate alternate route, quick certification. So they come and they take the same courses. They don't do the teaching practice, we call it internship, and they don't teach in a college course because they teach in their schools at the moment. They come at night, all my courses are at night, and they take the same courses. So we have a group of pre-service and in-service teachers, but it's better than that. Rutgers prepares doctoral students, PhD students. So if I have a PhD student who wants to work in physics education research, usually a former teacher, I only accept those who have teaching experience in a high school to later become professors who prepare new physics teachers. They also take these courses. So we have research experience, we have teaching experience, and we have these young, energetic people who want to be teachers. So usually it's from 10 to 12 students. Sometimes it's like 16, 18, which is too many. It kills me reading their homework and practicing stuff with them. My ideal number is like from 10 to 12 a year. That's how many are in the courses. But in terms of newly minted physics teachers, it's from 6 to 8 every year. Sometimes 10 on a good year, but it's rare. This year we graduated 8.
Muchas gracias, Eugenia.
You're welcome. I wish I knew how to say welcome in Spanish. I'm sorry. Okay. Okay. De nada. Thank you for your questions. Gracias. Any more questions, people?
Buenos días, ¿hay tiempo para una pregunta más?
I think we have 2 minutes,
por favor,
right?
adelante.
Bien. Bueno, capaz que la pregunta es corta, la respuesta puede durar mucho tiempo, pero bueno, que ella administre el tiempo. Quería agradecerle, obviamente, a Eugenia por este tiempo y también agradecerle a Daniel, a Álvaro, Martín y Arturo por esta idea genial que han tenido de invitar a Eugenia y, bueno, dentro de este ciclo, ¿verdad? Yo quisiera hacer una consulta sobre, si hay tiempo, me gustaría una respuesta cómo es a nivel universitario y a nivel de secundaria, pero bueno, capaz que sería muy extensa la respuesta, entonces podría conformarme con la respuesta a nivel universitario. ¿Cómo se realiza la evaluación de los estudiantes en un contexto de ISLE? ¿Hay una calificación final? ¿Se acredita a los estudiantes de forma que aprueben el curso? ¿Hay pruebas individuales certificadoras? Porque, digamos, yo, la parte de la evaluación continua y las rúbricas que tú nos mostraste está bien, pero además de eso, ¿hay una calificación final individual del estudiante con una prueba final? No sé si fue clara. Es eso.
Yeah. Yes. Very good question, and I really like how you worded it. In an ideal world, if I were to do what I want, there would be no grades. There would be pass or no pass. And that's how David Brookes does it, right? All his exams are pass or no pass. So and he uses the same rubrics to grade the written exam answers. And a student, if they, on the first try on the exam, basically, yes, there are exams, of course, right? And they usually 3 exams or tests during the course. I'm talking about college. during a semester. We have 2 midterms and 1 final. And different people do it differently, but the best approach is by David Brookes, who, and if you email me, I will connect him to you, and we'll also describe this method in our book about IEL. Every problem that the students have has a rubric, what is going to be evaluated, what they need to show. It's not the correctness of the answer. It's how clear you are, is how you argued in, it's a different rubric. It's not that the number is correct. It's that you showed your reasoning, the representations are consistent, it's clear to understand, or if the uncertainties involved, you evaluated uncertainties correctly. It's not about one right answer. But then the students has to get adequate on all parts of the rubric. And if something needs improvement or inadequate, the student fails. And then they have to take the exam again. So they get a new problem and they do it again. So this is a time-consuming process, and he has small classes, right? In the large classes, we are doing it with classes of 200, 300, 400 students, right? We have exams that are either multiple choice or open-ended questions that are all based on our approach. These are very different questions, though we have some traditional questions that you would recognize as something that all physics teachers do. But we also have specific questions that assess what the epistemic knowledge, right? And they're in our textbook and the active learning guide, and examples are in the IEL book. And then when you have 400 students, the exam students cannot resubmit, right? They can only resubmit lab reports, homeworks, and quizzes, but this they can resubmit. But the exam, if it's an open-ended, it's consistent open-ended questions, then the instructors who teach labs and recitations, part of their teaching load is to grade 1 question on the exam. Again, not for correctness of the numerical answer, but for the rubric that we use for grading. But in this case, students do not see the rubric. Multiple choice, and we have courses that use IEL with 700 students, is more difficult, right? So we have this very special multiple choice questions that assess reasoning. And an example I showed you, when it's not just choose the right answer, but choose the right answer with the right explanation. If you were to conduct an experiment to test this, what is the equipment that you would choose? And then you have a set of equipment, right? And you need to choose. And, if this is the data that you collected, that what are the patterns? And then we give them the patterns. So it's much more difficult, but it can be done. It's just the questions become different. Not all of them, about 60%. 40% are still very standard questions, but the majority of the grade comes from the reasoning part. And this is not an ideal world. Ideal world is David Brookes's world. In my classes where I prepare teachers, I don't have any grades. I tell them at the beginning of the course, everybody gets an A, the highest grade, because I do not believe that you want to be a B teacher or a C teacher, right? You didn't come here to spend $30,000 to become a bad teacher, right? I believe that you all want to be the best teachers you can be. I'm going to help you. You will resubmit and improve your work as many times as needed for me to say that it's perfect. You tell me when to stop. If you are exhausted and you cannot redo it anymore, you tell me. But I believe that you want to struggle until you're really the best you can be, because if you don't want the best you can be, you probably shouldn't be a teacher. So I kind of brainwashed them into this mindset of trying to be the best you can be. Not the best in the world, but the best you can be. And then I push them. And I push them and push them and push them until I know that this particular person cannot do any better than I say, okay, this assignment is done, move on. I can only do it because I have very few students. But each of those students is going to affect at least 1,000 people in his or her life. So I'm morally responsible for high quality, right? If I slack, I'll produce bad teachers, and then thousands of students will suffer. So I take it seriously. And I don't think that a grade, which has shown again and again and again, any grade has a negative effect on learning. A good grade, a bad grade has negative effect on learning, because if it's a good grade, then I don't need to do anymore. It's a bad grade, then I'm not smart enough, right? So in an ideal world, there should be no grades, but we'll live in a real world, right? So we try the best that we can, and that's what different people do. I don't know. Did I answer your question? Yes.
No respondiste mucho más que la pregunta. Muchas gracias.
Okay. Well, it was really great and an honor to be with you. And thank you for your questions. They were very insightful. What I want to tell you that I give these talks to many audiences, and you are the first audience that did not ask the question that everybody else asks. And I think it's because you understand that it's not an important question. And you want to know the question that everybody else asks and you didn't ask? It's the question, how do you cover the material with aisle? I have a long answer to this question, but a short answer, if you want to know, it doesn't matter what we cover, because the students won't learn, right? It's better to do less but well, and it's better to teach them how to learn on their own. And that's what we do. So whatever we don't cover, they can learn on their own. Well, thank you. Thank you very much. I think I'm losing my voice. I'm not used to speaking for so long, because all my classes is students talk and I just watch. Bye-bye. Thank you.
Para terminar, quisiera, bueno, volver a agradecer a la profesora doctora Eugenia Etkina por estar aquí por primera vez en Uruguay, aunque sea de forma virtual. Y la verdad, digo la primera vez porque la verdad que sería genial contar con financiación para que alguna vez pueda venir y dar alguno de sus talleres de forma presencial, tener el contacto con estos experimentos y interactuar y hacerlos de verdad en el mismo ambiente físico. Y digo, porque la verdad tuve la suerte de estar hace 2 años en un taller en Provo y fue fantástico con ella y con Goraz Danisic. Y la verdad que sería una experiencia, creo que notable para todos. Así que bueno, guardamos la esperanza por ahora, pero agradecidos enormemente por la generosidad. Solo quiero contarles a todos que esta charla quedó grabada, y que para que cuenten a sus compañeros, colegas, otros profesores que quieran escuchar a Eugenia, va a quedar grabado en el mismo sitio, en el sitio web de este seminario. Y para terminar, bueno, para retribuir la generosidad de Eugenia, quisiera pedirles la generosidad de todos si pueden abrir sus micrófonos y brindarle un aplauso sonoro a Eugenia. Muchas gracias.
Yeah, thank you, thank you, thank you. Thank you. Do not forget exploring and applying physics. Bye. Thank you.